Hello. Hello and welcome to this another video of multi-threaded programming in C. And we are going to study a lot of theory in this video and little bit of programming we will do. So first up is Amdahl's law or Amdahl's law, however you pronounce it. I don't know how to pronounce the name. So the thing is that you would expect that if there is one physical core of CPU, and if there is another CPU of two physical cores, then you would expect that with multi-threading, you will get twice the performance from the second CPU, but that is not true. The formula is given by this law that speed up is equal to 1 over 1 minus P plus P slash N, where P is the ratio of parallelizable code over the total execution time, and n is the number of processors the code can use. So clearly you see that it does not scale linearly. Okay. So we will study the reasons why that is not so. The most important part of that is critical sections, which we'll cover it in a bit. So first we go through this piece of code and we understand the different standard level functions. And we will see that this time we are not creating the pthread detached thread. We will use join. So we have four headers included. Let me get rid of this. So we have four headers included: stdr.h, stdlib.h, string.h, and pthread.h. We have a thread routine which takes a word counter argument and returns that argument as well. Whatever it takes, it just returns that, doesn't do anything useful. These macros we carry from the previous video. So we have a variable pthread t, which type, which is a thread ID variable. Then we have void pointer thread result and one status integer. So we first create the pthread using pthread create. The ID goes inside thread ID. It is an input variable, and we pass the name of the function which we want to create the thread with, and then we have now that is argument is null. Now, if the return status is not zero, we abort the program, printing the status and a message. And then we wait for the thread to over. This pthread join will wait for thread to complete. This is important because if the thread is not scheduled immediately, the main thread may exit before that thread can process. In the previous example of multi-threaded programming, which we did, we were exiting on the basis of keyboard input. So we had control when we can exit. So manually we could wait for the thread which was executing the alarm code. Okay. If you have not watched the previous video, you should go and watch it. Otherwise, you wouldn't understand the discussion. Then in the pthread join, we pass the thread result, and what will happen is whatever it is returning will go into this thread result. And again, if the status of join is not equal to 0, here main thread will block. And by blocking, I mean it will not be able to do anything until the thread routine function completes. And once the status is, we have the status, that is join is completed. Status will check against 0. If it is not, then it is a problem. And finally, we check the thread result for null because we passed null here. So we test if the result is the same. And if it is the case, we return 0 to the environment. Otherwise, we return 1. So let's see this program in action. Now, one thing I wanted to clarify in the last video, I was looking for pthread.so, but that is no longer a separate library. The library is built into the main libc library. So we compile this program without minus lp thread. werr minus std is equal to c23 and minus pedantic. Pedantic space lifecycle.c. And then we run this and we have the output. Now, if we want to check what it returns, so we see that it returns 0. That means this was what was returned. Now we want to talk about a bit of theory. So first thing is the state of threads. So threads of 4 states: ready, running, blocked, and terminated. When a thread is created, it waits for the CPU to schedule it. At that moment, it is ready. Once the CPU schedules it, it goes into running state. Now, while executing the code in the running state, it starts executing the code of the function. And for example, it might wait for something like network IO or disk IO, or it may wait for a mutex to be unlocked. So in those cases, it goes into the block state. Okay. And once it is unblocked from those, it goes into ready state and again into running. So this loop continues between ready, running, block, ready, running, block. And once while running, it completes its tasks or it is cancelled by another thread, then it goes into terminated state. Okay, if it is done or cancelled, it goes into terminated state. So that is the life cycle of a thread. Now, I wanted to talk about invariants, critical sections, or serial regions, and predicates. So, what is an invariant? Invariant is the assumption about variables in your code. For example, suppose you are creating a linked list, then you would say that the head of the linked list should be either null or point to a specific type of pointer. Okay, and that any node should either point to a node of same type or that should be null. So these are invariants of a program. It is quite impossible to, I mean, unless you are doing really trivial programs, any serious program will definitely make use of invariants. Now, what happens is that while you are programming, there are sections of code where you will break the invariants and then you will repair the invariants. For example, the head might point to a memory location whose next pointer will not point to similar node or null. That might be a case in your code. And then later on, you point it to null or similar node. Okay. So you repair the invariant. Such sections are all critical sections, or they are also called serial regions. Now, what happens in terms of multi-threaded programming is I will use the word shared state. So if there is a variable which is shared by multiple threads and you are modifying that variable, okay, you are mutating the global state. At that time, you would need to take lock. You would need to use a mutex lock, and then after modification, you uh, unlock the mutex. Okay, mutex stands for mutually exclusive. Now, between the code between these two regions will be known as the critical section or uh, serial region. Now, you can break all the invariants in this critical section and repair them however as you wish. However, suppose you have lots of threads then and they are all waiting on the same global mutex, or rather they are waiting for the global stage to be free so that they can use it, then you will see that the performance of the program goes down because only one thread is using it and other threads are waiting for it. For the similar reason, in Rust, you can have only one mutable reference by one of the threads and other threads will have to take immutable reference. Rust simply does not allow multiple mutable references. So you don't have data races in case of multi-thread programming and Rust. But in C++, you can have deadlocks quite easily. We'll see that later on. Now you see that because of mutex, for example, in this thread routine, you acquire a mutex lock here and then do something with the shared data, okay, with shared data, and then you do mutex unlock. So at this moment, when you are doing this work, the program becomes equivalent to single thread program because all other threads will wait unless they are doing something else. Okay. So that's why, because of lock contention, the efficiency will drop and numbers will come in picture. Now, because of this reason, on multiple modern systems where there are huge number of CPU cores available, we have a thread per core architecture where we do not share a state among multiple threads. Rather, they talk using inter-thread message passing. But that is an architectural question or architectural decision. Sometimes you need to take mutex locks, and sometimes your application allows to do set parkour architecture. That depends on what kind of application you are doing. All applications are simply not suitable for that kind of work, right? So with that out of the way, we were going to talk about predicates. So what is a predicate? Predicates tells you about relationship between the set of variables of your code. So in general, a predicate is a boolean. So the predicate could be like is header null of the linked list we were talking about. Are there 5 elements in linked list? So that could be true or false. Both the statements can be true or false. So these are the predicates of uh, program. So now we understand the relationship between invariants, critical regions or serial regions, and our predicate. That's how they relate to each other. So make sure that you are very careful when you are acquiring lock in a critical section or serial region, and try to take lock only for what kind of work you want to do. If you just want to read it, then you take a read. For generally, depending on the design, reading only does not require a lock. Locks are mostly required for writing. So later on, we will see different kinds of locks which we can take and how I can design systems around those different kinds of locks. So with this, I will end this video here, and I hope that you found this video useful and informative. So thanks a lot for watching the video. We will meet again after 4 days when we will actually look at metexes and locks in code, and we will look at working examples. So I'll meet you again after 4 days. Till then, stay curious, keep learning, and most importantly, enjoy.